and welcome everyone to the last part of episode 7. So now we get to talk about quasi-integrability, which is one of the big things in my dissertation. So it is said that all magic comes with a price, and unfortunately for us, it's now time for to settle our debts. As we saw in episode 1, for any odd prime number q and all t in z2 hat, the following formulas, chi3 hat and chi-q hat for q greater than or equal to 5, gave us the Fourier transform of chi-q in the sense that the limit of the partial sum of the Fourier series converged in the simple 2q-adic frame to chi. The existence of chi-q hat was surprising, seeing as this integral fails to converge. Indeed, as we saw in episode 3.5, we had the following, that the sum of chi-q of n from n equals 0 to 2 to the big N minus 1 was this, and so if we considered the locally constant function, the nth truncation of chi-q, the integral of this function was the average of this, which is that and that. If its basic facts of p-q-adic analysis is that this chi-q would be integrable if and only if the limit of this as n approaches infinity converged q-adically to a finite result. The problem here is that that doesn't happen. When q equals 3, this is n over 4, which does not converge 3-adically. And when q is greater than equal to 5, note that q plus 1 will always be co-prime to q. And as a result, even though this term is geometric, it will not decay to 0 q-adically. So just as an example, if q equals 5, this becomes 6/4 or 3/2. So that's actually something kind of weird. If q is equal to 5, this integral converges 3-adically because of the fact that, and in particular, its 3-adic limit is -1 over q minus 3. However, it does not converge p-adically for any other prime. And in fact, if p equals 2, then when q equals 5, this thing will diverge to infinity, 2-adically. So in this respect, the work that we did in episode 4 and the similar thing that we just did for that F series, polygenic F series in part 3 of this episode, we can think of that as a kind of renormalization. This term comes from physics, where in the path integral formalism of quantum mechanics, you take an integral over a space of functions. Unfortunately, function spaces, like the ones used in quantum mechanics, tend to not be locally compact, and so the standard theory of Lebesgue integration simply doesn't work because you need local compactness for the measures and everything to be nice. As a result, physicists make things work by just allowing all of the divergent quantities to cancel each other out in a way such that you end up with a finite result at the end, one that happens to be useful. We were doing something similar in our analysis of the Fourier analysis that we've been doing, but the difference there is that instead of doing a more hand-wavy cancellation, what we did is really it's an asymptotic analysis where we separated out the divergent component of our integral, meaning the part of this that failed to converge as n goes to infinity, and we showed that the leftovers, we in fact got something convergent. Indeed, here the divergent term is n/4, and here the divergent term is q plus 1 over 4 to the n. If we dropped those and made them disappear, we would get 0 and -1 over q minus 3, and if you notice, those are precisely the values that our Fourier transforms take at t equals 0. So we made our analysis rigorous by showing that, yes, if you drop the divergent term, then the result produces a Fourier function on z2 hat whose Fourier series recovers the original function, which is completely new, and it's an innovation that goes against what was traditionally expected in p-q-adic analysis, where this shouldn't be possible. So, and in particular, the the magic of this discovery is the fact that we made sense of the limit of this series with respect to a frame, rather than just picking a single topology for all of the points. Unfortunately, this trick does not come without cost, and so far I've actually been very careful to avoid discussing the cost of this result, but I cannot put it off anymore. Now that we have, and fortunately, now that we have frames at our disposal, we can discuss this issue in much greater detail. So, as we saw, because chi-q hat of t took algebraic values, provided we pick an embedding of it in the q-adics, and in particular, since the values of chi-q hat are in a 2-power cyclotomic field, our convention for choosing embeddings of roots of unity in the p-adics then gives us a unique embedding of, it's not canonical, it's just our convention. We have a unique embedding of chi-q hat in the q-adics for any q, and when we ran through the computation, we saw that chi-q hat ended up being q-adically bounded everywhere. As we saw in episode 4, this then means that chi-q hat is the Fourier-stieltjes transform of a 2 q-adic measure defined by our Parseval-Plancherel formula. In episode 5, we saw that if we considered the 2-adic Dirichlet kernel, D2n, we can consider the summation of the Fourier series generated by chi-q hat as an instance of Radon-Nikodym differentiation, with chi-q of z being the Radon-Nikodym derivative of the measure chi-q of z dz. Indeed, by using the above definition here of chi-q as a measure, we then have that, what we're doing here is, since D2n is locally constant and q-valued, it is continuous to any metric from Z2 to any metric completion of q, and because it's continuous, we can treat this as a measure. And the way that the measure works is that we multiply it by a continuous function, then we integrate, and so this can be understood here as a convolution of measures. And of course, the measure represented by a convolution of measures is the measure whose Fourier-stieltjes transform is the product of the Fourier-stieltjes transforms of the constituent measures. And that's exactly what we have here. The Fourier transform, and thus Fourier-stieltjes transform of D2n, is the indicator function of the set of t's with 2-adic absolute value at most 2 to the big N, and the Fourier-stieltjes transform of chi-q dz, that measure, is by definition chi-q hat. And so when we do this, we get that the convolutions of these two measures is precisely this thing. Since D2n is locally constant, this convolution is going to be locally constant, and so this is continuous, and thus it defines a measure in the standard way by we just take a continuous function, multiply it by this, and then integrate. But what's interesting here is that when we let n go to the limit, we were then taking a limit in a space of measures. And unfortunately, while that limit didn't converge in the topology of the dual of this Banach space, it did converge with respect to the topology induced by a frame. Before we could take this discussion further, I need to introduce some terminology. So let P and Q be primes, possibly non-distinct, with Q being possibly infinite. I say a PQ-adic measure d mu is algebraic whenever there is a function nu hat from zp hat to q bar, and a field k generated by taking q and adjoining all of the values outputted by nu hat, and an embedding of k in the algebraic closure of qq, so that d mu's Fourier-stieltjes transform mu hat satisfies mu hat equals embedding of nu hat. So this is very complicated, but it's the way to be technically correct about the following idea, which is, in my dissertation, I wrote that an algebraic measure is a measure d mu in PQ-adic such that mu hat of t is algebraic valued for all t. So this is a bit problematic because if you notice, since this is defined as an element of this space, by definition, mu hat of t takes values in the q-adic complex numbers. However, in the algebraic measures like chi3 hat that we've been working with, what we've noticed is that the particular values this takes in the q-adics are also algebraic numbers. So we can basically, what this is saying is that in an algebraic measure, there are two ways you can view its Fourier-stieltjes transforms outputs. You can view those outputs as being true q-adic numbers, or you can view them as being algebraic numbers. And so what nu hat here is it's saying this is the choice of an embedding that this is the choice of algebraic numbers that we identify with the Fourier-stieltjes transform of this function via our chosen embedding. So in this case, just for our measure right here, this measure as written, if we view its values as being algebraic in q bar, this would then be our nu hat. However, if we viewed its values as being 3-adic, that would be mu hat. And then the embedding is our convention of how we embed roots of unity in the 3-adics, and then that allows us to turn nu hat into mu hat. So if this is all too much for your brain to handle, just remember that an algebraic measure is a measure whose Fourier-stieltjes transforms are just output algebraic numbers as values. So yes, and that's just for people who don't care about the distinction between the different embeddings. A slightly better approach might be that an algebraic measure is a PQ-adic measure such that the Fourier-stieltjes transform of mu hat, the Fourier-stieltjes transform of d mu takes values in the intersection of CQ and Q bar. So the idea here is to take advantage of field embeddings. So as we said, for an arbitrary d mu, a mu hat is only guaranteed to be a q-adic complex number. It's not guaranteed to be algebraic, or let alone, or even rational for that matter. So as an example, let's consider the measure d mu defined by the following formula. Mu hat of t is 0 if t is 0, and if t is non-zero, it's the following sum. It's q to the exponent of the power of p in t's denominator to the power of n. In particular, so we see that when t is non-zero, if t's denominator is p to the k, then mu hat of t will be this sum, q to the p to the kn, which is going to, since k is going to be here greater than or equal to 1, this is going to converge q-adically. And in particular, we end up having that the number this converges to is going to have a q-adic absolute value at most 1 over q, because everything in this sum is going to be a multiple of q. So what that tells us is that the supremum norm, the pq-adic supremum norm of mu hat is 1 over q. So indeed, this is a measure because it's pq-adically bounded. However, this quantity, not only does this expression fail to converge in the reals, because q is greater than 1 and p is greater than 1, the value to which it converges in the q-adics is a transcendental number. So, meaning that there's no real quantity, or indeed, in any other completion of the rationals, there's no quantity that corresponds to this, except its unique copy in QQ. So a measure like this mu hat of t, this d mu, is inherently q-adic valued, and thus is not algebraic. This is in contrast to our chi-q dz measure, whose Fourier-stieltjes transform takes algebraic values. Because every metric completion of a global field like Q can be further extended to a metrically complete, algebraically closed field, we can then look at algebraic measures with respect to any metric completion of the rationals. And so with all that being said, we can now give a rigorous realization of our discussion of Radon-Nikodym differentiation of measures in episode 5, albeit of course, in a frame-theoretic context. So let's see here. Yes, let P and Q be distinct primes, and let d mu be a PQ-adic measure, which is algebraic. Suppose there is a number field K, a K-frame F on ZP, and a F rising continuous function G, such that the nth p-adic Dirichlet kernel, when convolved with d mu, we take the limit as n approaches infinity, and the result is F convergent to G of Z. Then I say that G is the Radon-Nikodym F derivative of d mu with respect to dz. More generally, given algebraic measures d mu and d nu, a function G is said to be the Radon-Nikodym F derivative of d mu with respect to d nu whenever this limit converges. Here, this is the measure, the mu measure of the p nth of the set of all p-adic integers congruent to z mod p to the n, and this is the nu measure of the set of all p-adic integers congruent to z mod p to the n. So when d nu is equal to dz, this ratio reduces to the case right here. And indeed, dpn convolved with d mu, by definition, it's p to the n times the integral of the indicator function of y congruent to z mod p to the n times d mu of z. Here, we can rewrite this integral. This is because this is an indicator function. This is taking the only values of z for which this indicator function will. This should be a y, not a z. The only values of z, actually no. This should be a y right here. This should be a y. Sorry, because there's a z here, so this is a convolution. This should be a y. So what this integral, this is going to be, the integrand is 0 if y is not congruent to z mod p to the n, and the integrand is 1 if y is congruent to z mod p to the n. So this integral gets rewritten like so, and here we just take the p to the n and write it as 1 over p to the n. This, of course, is precisely the Haar measure of this set, so that I'm going to use this as the Haar measure here. So this is the ratio of the mu measure of z plus p to the n zp divided by the Haar measure of z plus p to the n zp, which is precisely what we have here. So, and indeed, this is just because, as we mentioned in episode 5, our formalism for evaluating this limit, it's precisely the same thing as taking the limit of the Hardy-Littlewood, it's taking the Hardy-Littlewood averages, which we do in measure theory and harmonic analysis. So now we have a proposition. If the Radon-Nikodym F derivative of d mu with respect to d nu exists, it is unique. Proof? Well, since the Radon-Nikodym F derivative of d mu with respect to d nu is defined by the limit of a sequence in the complete metric space C rise of F, if this limit exists, it's necessarily unique. Now, before we continue, it's worth recalling the classical real-valued case of Radon-Nikodym differentiation. Let X and M be a measurable space, so X here is our set, and M is our sigma algebra of measurable sets, and let mu and nu be sigma finite measures on the space, with nu being a signed measure, potentially. So remember, sigma finite space is one that can be written as a countable union of measurable sets, all of which have finite measure. Then there are unique sigma finite signed measures, lambda and rho, on our measurable space, so that lambda and rho are mutually singular. Rho is absolutely continuous with respect to mu, and nu as a measure is equal to rho plus lambda. Moreover, since rho is absolutely continuous with respect to mu, there is a mu measurable function, f from x to r, so that rho is equal to f d mu, and nu is equal to f d mu plus lambda. So here recall that the mutual singularity of these two measures means that we can take our measure space and write it as the union of two disjoint measurable sets, E and F, such that every measurable subset of E has 0 rho measure, and every measurable subset of F has 0 lambda measure. The absolute continuity of rho with respect to mu, on the other hand, recall that that means that every set with 0 mu measure has 0 rho measure. This decomposition here is of nu into the sum of an absolutely continuous measure and a singular measure is called the Lebesgue decomposition of nu with respect to mu. Lambda is called the singular part of nu with respect to mu, and f is called the absolutely continuous part, or equivalently a rho is called the absolutely continuous part. A measure is absolutely continuous with respect to mu if and only if its singular part is the zero measure. We also say a measure is purely or totally singular with respect to mu whenever its absolutely continuous part is the zero measure. So classically, the one way to obtain the Radon-Nikodym derivative of nu with respect to mu is defined to be the absolutely continuous part of nu in the case where nu is absolutely continuous with respect to mu. So that is, in classical measure theory, the only time we talk about Radon-Nikodym derivatives are when the singular parts are zero. And then we have that, in this case, f is recoverable as the following limit, where it's the measure of the ball of radius x, of radius r centered at x, and this is if we're working over the reals, and mu is the mu measure of the ball of radius r centered around x. More generally, you can have the BRs of x, BR of x's be a family of measurable sets containing x, which converge to the singleton x as r approaches 0 in a certainly nice way. What's really cool, though, is that even if nu is not absolutely continuous, that is, even if this lambda is present, we can still use this limit to recover the absolutely continuous part of nu. In other words, we can think of this limiting process as a projection, one that kills the singular part and only leaves us with the absolutely continuous part. As a result, I'm going to extend the classical terminology and talk about Radon-Nikodym derivatives, even in the case where the measure being differentiated is not absolutely continuous. So the Lebesgue-Radon-Nikodym theorem is incredibly powerful and is a cornerstone of the study of real or complex valued measures. However, when we bring frames into the mix, things can fall apart in a truly astonishing way. We've actually already seen this happen. I've just avoided pointing it out until now. So, as we saw, since AQ hat has a Q-adic absolute value of 1 for all t in Z2 hat, and for all odd primes Q, our Parseval-Plancherel formula gives us a 2Q-adic measure. Let's call this measure dAQ. As we saw in episode 1, if we consider the resummation of this thing, we get the following function. Letting n append to infinity, we then get that the resummation of dAQ converges with respect to the simple 2Q-adic frame to this F series right here. So we then define AQ of z to be this function right here. And then we have that, just by the definition we gave above, that AQ of z is the Radon-Nikodym F2Q derivative of this measure with respect to the respect to the 2-adic Haar measure. Now, with all that done, it's obviously tempting to write that since this is the derivative of the measure, dAQ of z is equal to this function times dz, where dz, of course, is our Haar measure. Unfortunately, there are loads of problems with this. First, though, let's deal with the one case where things do work out. So blah, 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 blah. Yes, let F be a K-frame on Z. And so here because this was a little bit older, I'm using the first approach at frames where a frame outputs a field, F of Z. But all of this stuff I'm saying can easily be modified to the notion of frames that I constructed with semi-norms. So suppose that we have a K-frame which outputs F of Z. It equals a single metrically complete algebraically closed extension of the global field K. I should probably call this a trivial frame or something. And let's let d mu be a measure, let's say K-valued measure on the p-adics. And suppose that G is the Radon-Nikodym F derivative of mu with respect to the 2-adic Haar measure. If K is Archimedean and d mu is absolutely continuous with respect to dz, this is a typo, then G is integrable, and the measure G of z dz defined by the measure of E is equal to the integral of G of z times the indicator function of E dz for all this should be mu measurable. For all mu measurable E in ZP is then equal to the measure d mu. And on the other hand, if K is non-Archimedean and its residue field has characteristic non-equal to P, then G is continuous, and the measure Gz of dz is equal to the measure d mu of z. In other words, what we're saying is the way things work is when we don't need to appeal to frames, and the convergence occurs with respect to a single topology everywhere. To the proof, if K is Archimedean and the absolute continuity holds, then the Lebesgue-Radon-Nikodym theorem tells us that G is the absolutely continuous part of mu with respect to dz. On the other hand, if K is non-Archimedean with residue characteristic not equal to P, we then have our indicator function Fourier series, and now let's just compute the resummation of d mu. dp and convolved d mu is this, which is this, and then we write this as a Fourier series, and we exchange the sum and integral, which we can do because this is a measure and this is a finite sum. And then, of course, this is by definition, it's the Fourier, is the mu hat of t, the Fourier-stieltjes transform of d mu evaluated at t. This, of course, is going to, as n goes to infinity, this is going to converge to the Radon-Nikodym derivative of d mu. And since the existence of G means that the limit of this quantity converges with respect to f, with respect for all z, we haven't necessarily, this limit converges in our field K, the complete non-Archimedean field for all z. And so if we set z equals 0, we then have that this sum converges to something finite, which forces the mu hat of t's to converge to 0 in K. Since K is non-Archimedean, this means that this series converges uniformly with respect to z, which then forces G to be uniformly continuous, and which means that mu hat is the Fourier transform of G because G is then continuous. And so d mu equals G dz. To see why this does not apply, and so just in this context, remember that when we define a measure, was given any measure, we can define another measure by multiplying it by a continuous function. And so in that case, this measure in both the Archimedean and the non-Archimedean cases, this measure is defined by, for whatever function we're integrating against, we multiply that function by G, and then we take the Haar integral of that product. The problem here, and what happens with dAQ, is that because this is an F series, this is going to be rising continuous, but not continuous, and so that construction no longer works. Function times measure only gives us a measure, is only guaranteed to give us a measure when the function we are using is continuous. Here the function isn't continuous, so this is really just a notation. And the reason why it completely falls apart is, let's suppose Q is equal to 3. Then this vanishes, and so A3 of Z is identically 0. 0 is a continuous function, So 0 times dz would then be the zero measure. However, the Fourier-Stieltjes transform of dA3 is A3 hat, and A3 hat is not identically 0. In other words, what we're seeing here is that if we choose to interpret this literally as the measure induced by multiplying dz by this function, in the case where q equals 3, that function is 0, which forces this measure to be 0. However, we didn't define dAq by this formula. Rather, we defined dAq, and in particular dA3, as the measure whose Fourier-Stieltjes transform is A3 hat. Thus, this notation breaks down when q equals 3. When q is not equal to 3, the notation works, because in that case, actually, I'm getting ahead. So what we see here is that when q equals 3, dA3, the measure whose Fourier-Stieltjes transform is A3 hat, is not equal to A3 dz, the measure whose Fourier-Stieltjes transform is the Fourier transform of A3, which is just the 0 function. Faced with this situation, I came up with the following definition, and this is for my dissertation. Let G be the Radon-Nikodym f derivative of d mu with respect to dz. Then I say that d mu is f degenerate, or degenerate with respect to f, whenever its resummation f converges to 0. So degenerate measures are, actually I should qualify this. I should say that here d mu has to be a non-zero measure. Actually, wait a minute. No, it's all right. No, zero is included as a degenerate measure because we need to make a vector space of them. The point here is that degenerate measures are those for which resummation gives you 0, but the measure itself might not be the 0 measure. Indeed, the 0 measure is the only degenerate measure whose resummation is equal to itself. Yeah, so here's something that's really neat. If we proceeded like we did in episode 1, it can be shown that for q greater than or equal to 5, this f series satisfies these functional equations, from which we can then show that aq is 2q adically rising continuous. We can then repeat. In fact, the analysis we did in the last part of this episode, part 3, applies to this function, and from this we can then deduce that aq hat is a Fourier transform for aq of z. So this is actually really spooky. What we've just done, just to compare this. In the classical world, this procedure is equivalent to the following. We consider a sigma finite measure d mu on the circle, R mod z. We then compute the Radon-Nikodym derivative, g, of d mu with respect to the Lebesgue measure. We then compute the Fourier coefficients of g hat of n, of g, and then we define a new measure by saying the measure of any Lebesgue measurable set E, it's going to be equal to the integral of E, and here this is the nth partial sum of the Fourier series induced by g hat. And so we're taking the limit of that. This is completely analogous, it's the Archimedean counterpart to this construction right here. So in general, what this process will do is, because the Radon-Nikodym derivative will ignore the singular part, what we'll get is that in general, this measure is going to be equal to the absolutely continuous part of d mu. That is, d mu minus d nu is going to equal the singular part of d mu. And so, and this is indeed, since g is always going to be the absolutely continuous part of mu, this process will never result in nu equaling mu if mu has a non-zero singular part. When q equals 3, we end up with a comparable result. We consider our measure dA3. Its Radon-Nikodym derivative is A3, which is the 0 function. The Fourier coefficients of the 0 function are 0, and so when we resum everything, we get the 0 measure. So if we feed dA3 into this process, we end up getting a parallel of the classical result where we lose the singular part of our measure. So what this is saying is that dA3 is a 2-3 adic measure which is singular. And this is a new kind of singularity that hasn't existed before because, of course, we need frames to make sense of this thing. So, like classical singular measures, dA3 fails to be recovered when we run it through this process. On the other hand, what if Q is greater than or equal to 5? Well, then if we consider AQ, it's like say dA5, the Radon-Nikodym derivative, which we get by resummoning the measure, is AQ. We then compute its Fourier coefficients by doing our asymptotic analysis. And then when we do the resummation, we end up recovering dAQ all over again. So what this is saying is that for Q greater than or equal to 5, dAQ is behaving like a non-singular measure, whereas dA3 is behaving like a singular measure. Yeah. So what this all leads to is the observation that for Q, what this leads to is the observation that for Q greater than or equal to 5, we can define this expression as the measure dAQ, meaning that whenever we see an integral of a function times this, we're going to define that integral as the sum of the product of the Fourier-stieltjes transforms of this function and the function we multiplied it by. This definition is consistent because the Fourier coefficients of dAQ and AQ are the same when Q is greater than or equal to 5. So, despite the incredibly pathological convergence of the series defining AQ, the measure induced by AQ behaves like an absolutely continuous measure in that we can recover the measure from its Radon-Nikodym derivative and vice versa. This then leads to the idea of quasi-integrability. A function arising from the function chi, I say it is quasi-integrable with respect to the frame f whenever chi is the Radon-Nikodym derivative of some measure d mu. I then call d mu a quasi-integral of chi. So this, of course, just to go back to where we started with this, this then makes our chi q's into quasi-integrable functions. Chi 3, this function right here, if we sum the Fourier series, we get a measure, and thus we then say that we can identify chi q as with the Radon-Nikodym derivative of the measure with this as its Fourier-stieltjes transform, and likewise for chi q hat. However, then here's where the problem with this is. The quasi-integrals are not unique. And this is at first, when I was doing my dissertation, I was absolutely terrified by this, and I kept trying for weeks to figure out, or perhaps even months, weeks, to figure out if there was some way that I could recover uniqueness, but it's impossible, and so I just had to learn to live with it. Fortunately, it turns out to be, not only is it not a problem, it's actually incredibly interesting to explore, but I'll get to more of that in a bit. So here's how we can see the quasi-integrals are not unique. Let C be a rational number, and let d mu be the 2-3 adic measure whose Fourier-stieltjes transform is chi 3 hat of t plus c times a 3 hat of t. If we resum the measure, we then get that it's the nth resummation of chi 3 plus c times the nth resummation of dA3. Note that for each n and z, and for each integer n greater than or equal to 1, and z, and each 2-adic integer z, both this and this are rational numbers, and moreover, they converge to limits with respect to the simple 2-3 adic frame. The same holds for their sums, because again, they're compatible functions, so their sums are compatible as well. And so when we consider the 2-3 adic frame limit, we end up getting that this converges to chi 3, But this thing, this is the resummation of our degenerate measure, so it converges with respect to our frame to 0. So this term vanishes in the limit, and we're left with that d mu here is a Fourier transform of chi3 by our inverse definition of the Fourier transform. This is a function which generates a Fourier series that sums to chi3. Despite this fact, d mu is not the same measure as what we've been writing by chi3 of dz, because they do not have the same Fourier-stieltjes transforms. Their Fourier-stieltjes transforms differ by this term. What this then tells us is that, for as an example, both chi3 hat and chi3 hat plus a3 hat are Fourier transforms of chi3. In particular, both d mu and the chi3 of z dz are this is the function whose Fourier-stieltjes transform is chi3 hat. Both d mu and chi3 of z dz are quasi-integrals of chi3. The moral, quasi-integrals, although they are not unique, they are unique modulo a degenerate measure. And so this is the main result. Let chi be rising continuous and suppose it is quasi-integrable. If d mu is a quasi-integral of chi, and if d delta is a degenerate measure, then d mu plus d delta is also a quasi-integral of chi. Moreover, if d mu and d nu are any quasi-integrals of chi, then their difference is necessarily a degenerate measure. And so the proof, it's just by linearity. Letting n tend to infinity, the degenerate, so here as since these are quasi-integrals, these are measures, I think I might need to require that the resummation, I think I need to require that the resummations, actually, yeah. I need to require that the resummations of all of the measures involved are compatible functions. That's with respect to f. That's all that's needed, but then everything works. So assuming that d mu and d delta are quasi-integral and degenerate, and they're both that their resummations are compatible with f, we have this pointwise equality, and then letting n go to infinity, everything converges with respect to the frame. This converges to d mu, and this converges to 0. And since d mu was given to be a quasi-integral of chi, this thing is equal to d mu is equal to chi plus 0, and therefore d mu plus d delta is another quasi-integral. On the other hand, for this case, by linearity, the difference d mu d nu, well, this is equal to this, and these are both compatible functions for all n, and since they are both quasi-integrals of chi, their resummations converge to chi with respect to f. And so we get that this is f convergent to chi of z minus chi of z, which is 0, which then proves that d mu minus d nu is f degenerate. So this then leads to the definition. Let chi be rising continuous with respect to f, and suppose that it is quasi-integrable. Then, a Fourier transform of chi is and also all here we need for quasi-integrability. We need to require the measure to be algebraic so that we can recover frame compatibility. So actually, technically, it doesn't need to be algebraic. Rather, it's its partial sums need to the partial sums of its resummations need to be compatible functions. That's another way of saying it. Anyhow, so the Fourier transform of chi, if f is a k-frame, on ZP, is a function chi hat from ZP hat to k bar, the algebraic closure of k, which is the Fourier-stieltjes transform of a quasi-integral of f. So in other words, if we have our rising continuous function, which is quasi-integrable, to get a Fourier transform, all we need to do is find a measure whose resummation is f convergent to chi. Then that measure's Fourier-stieltjes transform will be a Fourier transform for chi. And so now we have just the following elementary properties. If chi hat is a Fourier transform of chi, and if chi of z dz denotes the measure whose Fourier-stieltjes transform is chi hat, we have that the resummation of that measure, f converges to chi. if chi hat is a Fourier transform of chi, and if mu hat is the Fourier-Stieltjes transform of an F degenerate measure, then chi hat plus mu hat is also a Fourier transform of chi. And if given two Fourier transforms of chi hat and chi hat prime, then their difference is going to be the Fourier-Stieltjes transform of a degenerate measure. So once we have one Fourier transform of a rising continuous function, we can get any other one by adding a degenerate measures Fourier transform to it. And in particular, we note that the set of f quasi-integrable functions is a vector space over K, and in particular is going to be a subspace of the rising continuous functions with respect to f, and this just follows by linearity. We can give a characterization of quasi-integrable functions as a quotient of vector spaces. This is how I do it in my dissertation. Doing so, however, requires a bit of conceptual gymnastics. Let's consider the constant function 0. By our definitions, any f degenerate measure d mu is then a quasi-integral of 0. As defined, these measures all have 0 as their Radon-Nikodym derivatives, and yet they themselves are not the 0 measure. So with the exception of the 0 measure, any degenerate measure cannot be recovered from its Radon-Nikodym derivative. On the other hand, for functions like aq, when q is greater than or equal to 5, the measures are recoverable. Because of this, rather than viewing quasi-integrable functions as functions of the p-adic integer variable, we're going to instead work with their Fourier transforms. This is because if I give you I can give you two quasi-integrable functions which are the same as functions, but which are the derivatives of different measures. So as an example, a3 hat and 0 are both quasi-integrals of the 0 function. However, they're not the same thing because one of them has a Fourier transform of 0 and the other one has a Fourier transform of a3 hat. So if we look at them on the p-adic integer side, we lose resolution and lose distinctions. But as long as we look at their Fourier transforms, we can keep their distinctions intact. So in particular, let V be the K vector space consisting of all the Fourier transforms of all the f quasi-integrable functions over Zp, and let W be the K vector space of the Fourier-Stieltjes transforms of all the f degenerate measures. Note that W is going to be a subspace of V. Then every quasi-integrable function, chi, belongs to a unique equivalence class of the quotient V mod W. So this theorem then gives us a purely algebraic construction of the f quasi-integrable functions. At the moment, though, much is unknown about quasi-integrable functions and degenerate measures. Some of the most significant outstanding questions about them are as follows. First, how do we show that a function is not quasi-integrable? This is a big one. So as an example, I suspect that the indicator function for a single point in the p-adic integers is going to be not quasi-integrable, but I don't know how to prove it. Because so far, the definition that we're working with would seem to require us having to examine all of the possible Fourier transforms and see whether any of them happen to sum to the indicator function in question. So next is let chi and eta be f quasi-integrable. Then it would make sense to define chi star eta as the resummation of the measure obtained by convolving chi and eta as measures. Does this sum always converge with respect to f? And in other words, what I'm saying is the convolution of two functions which are quasi-integrable with respect to the same frame going to result in another quasi-integrable function? And if not, what conditions on chi and eta are required in order for convolutions to preserve quasi-integrability? Another one, let chi and eta be quasi-integrable. Is the pointwise product, chi times eta, necessarily quasi-integrable? And if not, what conditions can be given to ensure that this occurs? How, and of course, with this is, how might we topologize the space of the quasi-integrable functions? Are there ring norms or ring semi-norms which give the quasi-integrable functions the structure of either a metrizable topological vector space, or a metrizable topological ring, or a locally convex topological vector space, or a locally convex topological ring? And of course, is there a way to determine if a function is quasi-integrable without presenting a formula for its Fourier transform? This would probably be one of the biggest improvements, because so far the only way I've been able to prove quasi-integrability is by going through the long, messy computation, like the one we did in the last part of this episode, and the one that we did at the end of episode 4, where we actually find a formula for the Fourier transform and manually check that its convergence occurs. And so this is an example of where I think things will get very algebraic very quickly, because what we would need to do is find a way to characterize them beyond just the bare bones of working with them manually. And indeed, is there a way to determine if a measure is degenerate without having to directly check that the convergence that its resummation converges to 0? Another thing that's really interesting is what do degenerate measures look like in general? What can we say about them? How do we find them? This is one of the reasons why I get excited about p-quadratic analysis as toward an insight on the Collatz conjecture. Is, I'm going to be honest, dA3 so far is basically the only degenerate measure, the only non-zero degenerate measure that I know of. It just so happens that the formula used in defining it gives us a degenerate measure, because it's precisely because of this formula. When q equals 3, this term disappears, and then this thing converges to 0 everywhere with respect to the standard, the simple 2-3 adic frame. I think that if we played around with the work that we did in part 3 of this episode, we might be able to find values of the parameters which set things up to become degenerate measures. Which then, of course, begs the question: is perhaps there's a relationship between characterizing the degenerate measures in various spaces, and understanding the behavior of the Collatz map and the other qx+1 maps. In particular, the fact that dA3 is a degenerate measure means that, and so this is probably the most important part, recall the Wiener-Tauberian theorem that we proved in the p-quadratic Wiener-Tauberian theorem that we proved in episode 5. What that said is, if we had a p-quadratic measure, d mu, then the translates of the Fourier-stieltjes transforms of d mu minus the x times d mu minus a constant x, though the Fourier-stieltjes transform of that measure would be dense in the space of sequences decaying to 0, if and only if the resummation of the measure d mu minus x evaluated at some point in z converged to 0. In other words, the main thing is, as I mentioned for the Wiener-Tauberian theorem, is that it only cares about convergence at any particular point. So what this tells us is that because dA3 is a degenerate measure, if we wanted to show something with Collatz, we can work with any measure of this form. That is to say, we aren't constrained to just show stuff involving the translates of chi3 hat. Because of the degenerate measures allow us to have freedom of choice, so that we can pick a different measure, and because this will converge when we do the resummation to the end result, we can also consider this when we're doing our harmonic analysis. And so, and we'll talk about this in the final episode, is that the fact that chi3 comes from the degenerate measure dA3, I think that's going to be very important for advancing our knowledge on the Collatz conjecture, because it's an algebraic relationship. It's about involving the nature of these F series and the way they interact with one another, that tells us that chi3 and its Fourier analytic properties, there's a lot more flexibility between them among them than there is for chi q when q is greater than or equal to 5. Again, another open question is, can you find me for each odd prime q, can you find a non-zero degenerate 2q adic measure which is degenerate with respect to the simple 2q adic frame? That is to say, what is the analog of a choice for A3 hat when we replace 3 with an odd prime q? When we replace that's greater than or equal to 5. If we replaced it here, chi q hat would resum to chi q, but CAQ hat would resum to CAQ, which is non-zero, not identically 0, because q is greater than or equal to 5. So figuring out what the analog for A3 hat should be when q is greater than or equal to 5 is another open problem. And so the quasi-integrability, this is the big new part, because this is what allows us to extend the non-Archimedean and that analytical work. It shows that there's a lot more to be discussed about regarding non-Archimedean valued singular measures than was previously thought. Near the end of his 1960, is it 1960 or 1970? 1978 book on non-Archimedean functional analysis, Van Ruij just remarks that the theory of Radon-Nikodym differentiation for non-Archimedean valued measures is very poor at the time, and although some progress has been made in understanding Radon-Nikodym differentiations in the ultrametric context, the PQ adic case, where P and Q are distinct primes, remains just an exception that no one seems to be able to handle until now with my work. So that'd be something interesting to look forward to. Now, so with that, we are now done with episode 7. And all that's left is the final episode, episode 8. And this one is going to be really fun, because now that we've gotten to the top of the mountain of all the stuff that I'm working on, I am going to then start showing you the current stuff that I'm actively exploring, and my ideas for how we can use this stuff to perhaps better understand the Collatz conjecture. Right now, one thing that I'm really excited about is that those connections to Berkovich spaces, they turn out to be much richer than I thought, and it really could end up being something quite useful if I can figure out how to make it work. So that hopefully I'll be able to include that. I'll also be talking about the adels and integration over the adelic solenoid, as well as exploring what I would call the Tauberian spectral theorem, which is what we get when we combine the correspondence principle with my p-q-adic Wiener-Tauberian theorem. And I'll show how that then leads us into discussions of cyclotomic extensions of q-adic fields, and it ends up turning the it ends up reducing the Collatz to a problem of solving a large number of congruences modulo powers of q simultaneously, which is absolutely transcendence theory, but just a non-Archimedean version. So see you then. It'll probably take a while for me to prepare, but hopefully it'll be worth it. Bye.